Greetings again. This is our October 30th class, and in this lecture I'm going to talk about kernel commands. So in our last lecture we covered the process of bootstrapping. Let's actually switch this diagram. So we actually finished our discussion of how bootstrapping works, and that's this green, the yellow area right there. And then now we're going to switch our focus to kernel commands that essentially provide us the capability to process information within the core as well as between the disk space here and the core space. So, excuse me, within the disk memory we have this kernel program, which would have been by now loaded into the green space here, the core space, and that kernel in the disk space occupies locations that would begin at 1000 here. And of course, by the time it gets copied over here, its location will shift, the top location here, to 700. Again, that's a hexadecimal number. And that's where things will be executed from. So when you think about the program counter, as far as executing commands out of the kernel, that is the sort of reference for that. We don't really execute things out of the disk memory, but we execute them out of the core memory. So that's something we need to keep in mind as we delve into the code later on. And the 5 commands that we covered were load, save, execute, read, and write. So we're going to take a look at maybe a couple of those, if time permits, maybe more than that, and then see how those commands are actually coded in the kernel version of VESP source code. And hopefully you'll be able to go through those yourself and relate to the discussion today. So let us now switch to, and we may get back to this place occasionally to perhaps explain things a little more pictorially, but I guess it'll be best if I switch now to the source code where we could see how things get organized. Because of the constraints that I have in my current location, I may try to keep this discussion as brief as possible. So let's keep that in mind. And now let's in fact move this up a little bit. This is where the load loop apparently is located. I'm going to go up a little bit here to sort of like find that first place where the storage, the hard disk space, is populated with this kernel code. Now, keep in mind that this portion of the source code is in the initialize function. So the initialize function basically takes care of the creation of the kernel code. So now, whereas we used to store things into the bootstrap memory over here, because that was part of our extended bootstrap code that VESP would have executed to complete the bootstrapping process, all of this stuff here. Now we're going to switch gears and we're going to put things into the disk memory. Again, this is all, as you can see here, part of the initialize function. This initialize function is there to essentially set all the locations in the bootstrap memory, and then after that put the stuff into the hard disk memory. And of course, if you look at our main program, you'll see why it's critical to understand this. The main program is really simple. All it does, it initializes places and then it bootstraps. Of course, we go on to other things from the bootstrap that is towards the bottom of the source code. So what is really critical to understand then is that the initialize is the first thing that the main function calls, and in that process a whole bunch of things have get initialized. And so the bootstrap was the first part of it, and then then once this is completed, then the simulation of VESP, the kernel, effectively executes the bootstrap code, and then that includes copying things into the kernel space within the core. And once that is completed, then we're looking at basically the commands within the kernel. Of course, they have to be created first, and that will have to take place within the initialized function. By the way, this portion that you see here, right there, is the loading of the kernel that is part of the bootstrap process. So this is distinct from the kernel commands that we're going to create now and place in the hard disk of VESP. All this is doing is just copying the stuff that is going to be located in the bootstrap in the hard disk memory. Now, since this is all initialization, and since the execution of these steps comes later, when we actually look at the bootstrap process and so on, so the initialization process being done in here and in this order does not necessarily mean that we have an issue with copying the kernel here and then defining its contents, down here, for example. That doesn't become an issue because we actually are creating these instructions or these programs, but their execution is handled through the code that we actually have placed towards the bottom of this place. In other words, all of these things are properly executed in the right order, that is, through this process, this bootstrap process. So initialization, all this does is just puts the numbers in there, basically the programs that we're creating, and then the copying wise, the execution order of the bootstrap and the copying of the kernel, and then eventually execution of kernel commands is all controlled under this bootstrap processing. So let's see if we could follow this a little more. The bootstrap process, once it is over, we will end up having everything copied into the core, and so we could actually get started with the process of executing commands. So the locations in hard disk will begin at 1000, as I said earlier. And we're going to populate this area now with the code that would relate to all of the commands that we could execute out of VESP's terminal. And among the things that we have to do would be to put certain prompts and messages to let the user respond to, and so those things would include, for instance, the prompt that says enter, and then we would have to give at times a signal for what kind of address that we would need for that particular command, if in fact there is any such need, and that could be what we call the D address, or it could be the M address, D meaning disk and M meaning memory. So what these particular pieces of code do, they actually initialize locations to these messages, and these messages will then be displayed based on what commands we execute. For example, if we're doing a load, we may just prompt the user with the D address so that we know exactly from what part of the disk that information must flow, and then we need to also ask for an M address to see where things come from, go into in the core memory, and so that's part of that. Now, once this is all completed, and you notice that we began populating the very first location in the disk memory, we can then move on to the source code in, of course, VESP at this point in time for those 5 commands. Now, there's one other important piece of information here to keep in mind, and that is this. even though we write things into the disk memory, the code that we're generating here will be executed out of the core memory. And so there's a translation of addresses. Now, the disk itself will contain this code that we're creating at locations that begin at 1000. That's hexadecimal. Whereas the code that will be residing, this same kernel code that we would have a copy of in the core memory, it'll actually populate locations that begin at 700. So that translation has to be kept in mind, especially as we write this code. There will be certain places where we may actually make, for example, conditional jumps, etc. Some other address values may have to be introduced into the instructions. When that happens, we need to take the 700 as our reference point. So you will see that, in fact, what this comment section here, these numbers you see, they actually track the displacement of these instructions in terms of their locations, as if they are actually located in the core, so that we would be able to tell exactly where to branch to. So like 1000 is 700, the next location is 701, whereas this is 1001, and it's 1002, so it'd be 702, and so on. You can see how that tracks. Here's 1002, here is 702, and then it goes like that, 1003, 703. And again, this is important because we're going to have certain places we're going to have to branch and do other address translations, and we just have to look at these numbers, and that's how we write them. I'll point them out to you as we go down a little more. This portion is trivial. These are all load commands, as you can see. They begin with a 2, and we just keep putting more and more stuff into these screen frame buffer locations. 23C0, 23C1, and so on. So we're basically writing these comments into our frame buffer. By this time, it looks like we've actually switched to page 3. That'll be page 4 here, and it goes like that. When I say page, I really mean like line, and then we may also skip certain places. Keep in mind that we have the screen itself is made up of 16 lines of 64 characters. Okay, so this portion is just there to put these messages up and display them for the user. Now here's the load loop. Another critical piece of information is this. We're developing the source code in VESP in here, which you'll see here, and somewhere down here. That piece of code right there. And this is what VESP does when actually we want to load something. Now, of course, since we are doing a simulation here, we're going to have to execute this code out of the simulation source code, which is the C code that we're using. So that means that somewhere down towards the end of this file, we need to have a function called kernel that will manage, supervise all of the activities of the VESP, and these include commands like load and save and write and execute and read. So this piece that I just highlighted here is the load portion of it. This is the load portion. And so, of course, we recall that we used letters L and S and E and right and W and R to make a reference to these commands. And so that parsing takes place in this code kernel here. And you'll see this now, right there. And now the kernel, of course, is kicked into action once we complete the booting process, and that was this code right here. So let's just remember now, we had the bootstrap at the top, right here, which is just there to copy that extended bootstrap code into the VESP memory, the physical memory, the core, and then it calls boot here. The boot gets called, boot goes into action, boot does all it has to do, which is to actually copy things, including the kernel itself, into the core, and then display messages relating to that. And then once that gets completed, at the very bottom here, we call the kernel. So that gets taken care of. Now, so by the time we finish these two functions, execution-wise, we go into kernel. We get into there. Now, the kernel itself is going to now manage all of our activities, and among those are those 5 instructions or commands: load, save, execute, read, and write. So, and other things including, for example, enter a command code. So when you look at the kernel, you will see that it's going to execute each of those 5 commands, which essentially begins here. And those cases will pertain to what kind of command that you want to execute. But the first thing is to display the message enter, the prompt message to the user, so that the user knows that in fact it is in that state now, that the kernel is operational, and now it can actually go ahead and perform a command itself. So initial piece here is just like the process of displaying something, and then the program counter is set to 700 because that's where the enter message was stored, and then we just issue a main cycle loop which runs for about 6 commands. 6 cycles, meaning that we're going to get this word letter ENTER. I guess that must be something that probably is left out here, something like this. So it'd be 6 characters displayed once this for loop is completed. And then we display that, of course. Once we put it into the frame buffer, then we actually display it right on the screen. Now, after that, we read in one more character from the screen. This time we actually get a character from the screen, from not the screen but from the terminal, which really is our kind of screen in a way. And that now is stored in location 10. And we're going to look at that location, which is this same location into which we get a character in, to see what command we would execute. So one of them will be L for load, and another one would be save down here, right there, and another one would be execute. That will be here somewhere, right there, and then read and write. Here's read, and then here's write, somewhere here. Let's see where it is. Right there. So those are our commands. Now, so the critical thing to understand maybe here is how we synchronize these operations that take place here with the execution of machine instructions within VESP. So since this is the emulation process here, since we're emulating the process of, let's say, load, we're going to have to synchronize the process that VESP goes through with what we do here. What that means is that when we are loading, for example, as in this case here, we are going to have a certain number of let's call them operands for lack of a better description, from the disk space into the core space, and the way that we're going to determine the end of that loading process is by way of inserting quadruple Fs into the last operand space. So we will only terminate this loading process when upon seeing a FFFF within the set of locations that we're trying to copy from or load from the disk space into the core space. that means that somehow we need to predict, or we need to actually determine, not predict so much, when that happens. Now, VESP itself is going to do this check, this test, whether it's actually reached the end of the file or the list of operands that need to be copied, and that means that it's going to compare whatever is currently being transferred from the disk space into the core space. It will check to see if it's actually equal to FFFF. And so now this code here, all this is doing is simply testing to see if that condition actually happened. The first thing that the load does is, of course, to get a bunch of numbers into to determine where the load be processing the operands in the disk memory to put them into the core memory. There are these places, like location from 10 on to 13, where the disk address will be specified, and then there shall be 4 more locations where the address for the core space will be specified. And so that is precisely what happens in here. And so we execute here for about, I guess, let's see, somehow, I think this is about 10 instructions long. So this must be like D space or D address. And then same way over here, we execute the same number of main cycle here. And that begins at 795. Now, if we go back to here, you will see where they are. Now, over here, before even we begin the load loop, right there, you could see that there is this M address and there is this D address. So this is what we were doing down in the kernel portion. Right there, this begins at 781. And it lasts for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 main cycle steps. This is what we're going to display in there. And then we're going to read something out after that. And this is also, I think, the same number of locations. So one begins at 781, the other one begins at 795. These are basically load commands that we have to execute to do what's called a load command. So let's go down there again and see this briefly within the kernel itself. You could see that within the loaded portion here, the case statement, we are starting at location 781. This is where the first address is, that is the D address, and we executed about, like we counted there, about 10 instructions just to get those letters out there. And then we also do the same starting at location 795, and then we read the stuff after that. So we display by way of these main cycle executions. Of course, upon doing that invitation, the prompt, we then go out and actually read 4 consecutive characters. These are basically the locations that the user would specify. This is for the D address. Let me just actually say this here. D address. And this would be the M address. So that's how we get to read them. Now that these are characters, so we have to actually pack them from ASCII to hexadecimal. This is what this step does. So it kind of like takes these hexadecimal digits in ASCII and creates a hexadecimal number out of each. By the end of this process, of course, and you could go through this computation here. I'm not going to bother too much with this because it's a simple translation of ASCII characters into an actual hexadecimal address. That's just that translation, and then after that we're going to have some packing to do. That packing will just simply create the disk and the RAM addresses we need. And once we get that done, then we jump to location 800. This is where the loop, that actual command, begins. So that means that we have to go back here and then watch to see what happens at that place. Now, you could see that within this portion, we really have broken, sort of like decomposed the execution process into at least one step here, right there. That's called initialize IX. And then within the while loop, we have a 3-step, or in fact a 4-step process, one, and then a conditional statement, which will then put us into a, I guess, another 4-step execution. And if that's not the case, then we get to execute some 8-step process here. And these are basically main cycles that we're executing out of VESP. So we start out with 4 main cycles. We then go into the loop. And the reason that we're in a loop, we don't really know where this loading will end, so we're going to have to test that. And that testing takes place through this register called A. And in order to actually get to that place even, we got to have about 4 main cycles consumed. And then we will be ready for this test. If that's the case, in other words, if you find this thing to be 0, that means it's the end of the file, if you like. It's the end of file sort of process and decision here. Once that gets done, then we need to execute some 4 more instructions and then be done. We break out of there. Otherwise, we continue 8 more steps. Of course, either we do this or we do this, one or the other, and then go back to the loop. So this really is the synchronization process that I talked about. What exactly that means is that, in fact, as it is commented here, at least in this first case, we're initializing the IX in the initialize function. We are going to do this process when, in fact, we get to this load command. So let's go back to that area and then see how that really is synchronized with this. So right there, somewhere here, there's a loop. There. There's the load loop. So the first thing that we do is to initialize the IX to disk address. And this is the instruction that we get to execute. Now note that this is moved to 1100 in the disk space, and that of course means that we're in location 800 in the core space. That's why we initialized the program counter to 800, because this is the first instruction that we're going to execute. Once we get this done, then we will put in quadruple F into B, and we'll perform a subtraction, and that subtraction will actually take care of that A register being 0 or not. So basically we're looking to see if we reach the end of the file or end of the data that we're trying to, or the operands we're trying to copy from the hard disk. So the process is to put the FFFF into B and then load the next, I call this next instruction, even though it could be next operand, into A. And then of course save that operand. I guess this is the loading process right there, and then we save that into location 18, because we're going to compare, check to see if that's actually equal to 0. You remember that place where we're testing something for 0, that that actually is not, that's not where we're going to make the comparison. We're going to make the comparison out of 0, but this is the value that we have to copy into the core, so we're kind of saving that into that location 18, from where we're going to have to copy that value, instruction, data, operand, etc., into the core memory. So you could see that saving takes place, because we're going to destroy it in the next step. As you can see, there's a new command. This is one of the new commands that I actually talked about in our last videotape class. So that does take care of us. That takes care of the subtraction process without having to do a complement, two's complement, and addition, and so on. And so this is simple subtraction right there. Just one opcode takes care of the subtraction. Now this is where we would arrive at having completed the first step. Let's see how many instructions we execute after that. So here's one. Here's a second one. And here's a third one. And here's the fourth one. So what the kernel must do, having initialized IX to the disk address, it must execute 4 more instructions to get down to here, so that it can now test whether in fact A has become 0. So that's what was happening in the kernel here, as you look at this load down here. First, within the loop itself, let's see down here. Okay, let's go down here where the while loop starts. So we initialize the IX, that was one step, and then we go out and do 4 more steps within the while loop. Now we can test if A is equal to 0. So by the time we finish the execution of 4 consecutive main cycles, we would have gone to that point where A is now set to A minus B, and therefore we can simulate whether in fact the thing has become 0, which is to look at A and say, are you 0? If so, we're going to have to execute, branch out of there, and that will require 4 more instructions to finish this whole process. If not, we're going to have to do about 8 of those. So that if statement is made manifest over here as well. Let's go back again. So you really have to keep track of these things to understand how these two things are synchronized. Right there, we were doing this on the simulation side. Now here, we would have reached this place to test that condition within the simulation code in the kernel function. And so that would have taken us 4 steps down, because we would have executed 1 here, 2, 3, and 4 instructions. And then if in fact we had found this A to be 0, we would have then done this instruction, that is to set the exit address. By the way, this is 815, that means we're going down here somewhere, here. That would be 1 instruction to execute, and then we would execute a second instruction, and then that will be a jump instruction. Now when we get down to this location, this is, by the way, a jump via this register B. That's how you actually jump. This is how you set up the jump instruction here. And this is jump if A is equal to 0. And that will take us to this location. Now when we get down to here, we execute. That would have been actually our first instruction after this, A equals A minus 1. So this would be like 1 instruction there, and then second instruction, and then we're down here at location 815, right here, that one. And then we would basically wait for no operation. So 2 more instructions here and 2 there. That makes it all 4 in all. That is if in fact we did find that the value in A is equal to 0. That means it's time to bail out. What this actually does here is that it makes the it copies the very last operand or the data or the instruction from the disk memory. That's the way this loop is set up. 1 last operand remains, and so that gets completed in here, and that gives us 4 commands to execute. If in fact we hadn't done this, in other words, if we hadn't found in the simulation section in the kernel function that A is equal to 0, we didn't find that to be the case, we would actually still set up this exit address and go through this That would be 2 instructions, but we would not be jumping down here. Rather, we will go through here. So that would be like 2 instructions. After that A equals A minus B instructions execution, we will have consumed 2 more instructions, and then we'll just do the rest of it, which will actually be all about now updating I guess the address within the IX to do the copying. So the first part of it was to bring the operand from the disk into a temporary location, which will now have to be copied into the core. So we consume 2 instructions in here. After this, now we're going to do some more. So 1, that is 3, this is 4, this is 5, this is 6, this is 7, this is 8. And that is exactly, that number 8 is exactly the number of clock cycles here, or the number of machine cycles that we have to execute. If you just remember, there was that 8 in there somewhere. Let's just find that out. Here's the load. Let's execute. There's a load here somewhere, right there, within the loop. How many times we go over? If in fact we didn't find the A to be 0, we actually go out from 39 to 46. That is 7 plus 1, that's 8 machine cycles. These machine cycles are executing those 8 instructions that I just counted. 8 machine cycles have to be consumed for us to get through those steps. So I think this should be fairly clear now. This while loop, once we initialize the IX, is simply emulating the process of going through this VESP program, whose sole duty is to copy things from the hard disk space into the load space. I mean, it's the physical space, the core. Okay, and since we can't, it's not like a straight line program. There is a breakpoint there, a conditional statement for the machine code, where we're checking to see if something is equal to FFFF, and we have to stop there. We need to break this simulation code also into 2 portions within the loop. We get down to a point where we have to first do 4 instructions, and then only then we can determine if A has become 0, because we just completed here, of course on the machine side, the execution of A equals A minus B. That's the last main cycle will take care of that. Now that it's been done, we're going to have to see if actually A has become 0. If so, we then go out and finish the process by way of 4 more instructions. That's how we end it. If not, then we do 8 instructions. So these separations are necessitated by the fact that we really have to watch our machine code as we simulate it break into these different directions or branch points. So this is really how this load process works. To load, you just have to figure out where you begin, and then how many times you have to go from the starting point on the disk memory side, and then do that via the same index register. That's why we had to save IX up here, as you can see, like right there in this portion. We were saving the IX because that IX is actually pointing to the location in the disk space where our next operand or the data is residing. But now that same IX must actually be pointing to where we would keep the running location, running address of the in the core memory where things will go in. So you can see that it's all about saving and loading the updated, or loading so saving the disk reference point, and then loading the core reference point, and then copying what is actually in temp into where that new IX will point to, and then once the IX is updated, because where we executed one of those MXF or MXT instructions, IX would have been updated, and then saving that for the next round, and then restoring the IX to the disk space address location, and then jumping back to the loop. This is what these instructions basically do. And that's a loop, basically. But the end of the loop is determined only when we check this A, which is holding the current data, versus FFF. And of course, to synchronize the process of execution within this load VESP code, we need to go into the kernel portion and then time it so that these instructions, the chunks of instructions, are executed in the right number, in order to make this testing of something being 0, and then based on the outcome of that, whether we do 4 steps or actually 8 steps, those decisions are made within the kernel function for us to emulate these steps. So the emulator is really, maybe I should call it simulation, is just simply respecting the breakpoints of the machine code. I think this is critical for you to understand. The synchronization is the most critical part of, I think, this whole process. If you understand this, the rest should really be fairly straightforward. All of the other commands are no different. Execute is basically very simple. Let's actually take a look at execute. Save is just the same thing in the opposite direction. But if I look at execute, execute is much simpler. All we have to do is just put into what's called the location B the address that the user will type in, like this, and that will go into location 10. That's where it's actually grabbed via the kernel interaction, and that address then goes into location 1, and this branch 7800 simply jumps to whatever address is actually stored in this location, and of course that gives the control to VESP, and that's what execute does. Once you go to this location, then you have a bunch of things to execute, and that execution, of course, is going to now respect whatever comes in that set of spaces that the user entered. And of course, unless it ends with a halt instruction, then kernel will keep executing that particular sort of like program. So this is really simple, because all we do is whatever is entered through the prompt into this B register, and then this 7800 is a jump instruction, which makes things which actually forces VESP to jump to a location that and whose address is basically stored in B. You can see this if you go back up here in the representation of these instructions. Let's see if I can quickly find it. Let's see, where's that? There must be some hexadecimal notation for this. Seems like I might have to do this a little bit. Okay. Let's see if I can find this quickly. There's the hex code right there. So now look at this hex code. We said it's 7800. 70 is halt. It's right down here. Take a look. Right there. Jump. Via B. 78. The 2 zeros are just a postfix to make the number of hexadecimal digits equal to 4. So jump via B is 7800, and that's what we're doing down here. Right there. Execute. Right here. 7800. So that, of course, has to be matched also in the kernel. There is an execute process here after save. Execute is really simple. All it does gets an address where the execution of that particular piece of code will take place, and it actually makes it into an ASCII code, the hexadecimal code, packs it, and simply goes on to execute it. Just this step. So 2 instructions is all we have to execute. One is to load something into B, as we just saw, and then jump. And then after that, while VESP reset equals 0, continue to execute. This is really where the simulation takes place. This is clear to 0 because we could actually execute another program after this is done. This is really simple. Execute two instructions. One was, as we just saw, if we go back, right there, one was to initialize B, and the second one is to jump. Those are the two instructions, and we're executing those when we get down to here, right there. Just two instructions, right, not there, but a little bit down here. Two instructions, and then once that is done, we go into the actual execution, because we know where the program counter is pointing now. That's done by these two instructions, the main cycle that we execute here two times. And once the address is known, once we know that it's the right address, that's actually user provided that address to us, now we go out and do the execution. And that's an infinite loop in a way. Until we encounter a halt instruction within the code itself, we're not going to be able to stop. And of course, once we get this completed, VESP reset would have been actually set to 1 by way of a halt instruction, and then we clear it to 0 for multiple executions. Otherwise, we won't be able to keep in here because we need to have a halt instruction. We would have actually had to have this equal to 0 to maintain this after halt instructions execution. So I think this is about it for today's lecture, because the rest of it is really very analogous to what we've done. There is what's called a read and a write process. In the event that we're reading from the terminal, so we don't really have the second address, so the read code is a little simpler. Write is the same way. We're writing into the terminal, and those things will basically be done through these loops. So here's, for example, the read loop here. Should not be as long, except that we have to provide this enter next code comment. But the loop itself, right down here, should not be as long. We still initialize, we still make the comparison. These remain the same. But the rest of it is, we could use, for example, the IX register without having to save it or restore it, because there's only one set of locations that we're actually, when we're reading into the, let's say, core memory. When we're writing, we are writing from the core memory. So those things would not require us to save the IX register. In the case of a load or a save instruction command, we actually had to do that because we have to use the same IX to go back and forth. One, to keep track of where we're loading things from in the case of a load instruction, and then in the once we get that done, then we have to keep track of where we want to load the thing into. So we had two places to keep track of. Now we're only keeping track of one place, and that is that's the core memory. Whether we're actually writing from core memory into the terminal, and that is the terminal always, or whether we're reading from the terminal into the core. And only one index would be required in that case. So that should be fairly straightforward. And once you get this going, I guess the rest of it is basically really what we did in class 2 classes ago. I guess we did do that. Okay, so now I'm just going to see if I can actually quickly compile this and then somehow be able to see this. So build succeeded. If I could get this come up somewhere right there. VESP is booting. And so this is what we did, like for example, if I were to read something, it's going to ask me, memory address, and I'm going to just create something. So I could put, for example, 0A00, and then it'll say enter next code. This is as if like it's taking instructions from me, and I can type in, like we did in class, something like this, and then we could do maybe an add, and then we could do halt, and then we put FFF. This is when it knows it actually has to stop, and then it says now enter. So we can then say execute, and then it'll say M address, so we put 0A00, and then it executes to a halt because we put the halt instruction at the end. It's like 7000 here. right there. So this is how this thing works, and I hope that you go through these examples yourself. Start running and playing with the kernel version of VESP, which I think you'll find pleasant to work with once you understand how these synchronization processes work between the kernel function and the 5 commands that have been coded into VESP via these places that we saw. Just like this was the read one that we did, and in fact we did the read. It went through this place, this process right there. And then the write loop works the same way. If I were to display something, for example, I guess I could still do that. Let's see. Oh, at this point in time, reached actually. Let's see if I could see this where it goes. Yep, here's the enter. So if I actually say write at this point, we'll just ask for the address. I guess I could say 0A00 and not displays what I have actually entered. So now we have a kernel running on VESP, and that's kind of nice to know because we had really built this from the ground up. VESP is a machine that knows only machine instructions, and now we give these letters like W, L, S, E, and so on, and R, and it knows what they are, and actually does almost all of it except our simulation process. This is not a real chip by way of machine code. If I didn't have to, we didn't have to simulate it, we would actually just let the chip complete all these steps by itself, and therefore we would not really have these functions separately monitoring our actions. So hopefully this discussion will help you grind through the kernel version of the code, and when I get back, we will pick up the interrupt version of VESP. But of course, between now and then, I'm sorry, we will have a test coming up on Wednesday next week, and then prior to that, there will be a review class. Hopefully, I'll be able to get Poya to manage to come to class. If that doesn't happen, I'm going to have to send you maybe another video class where we could do the review itself also on the video, and I can highlight the kind of things that you probably will have to pay attention to. We'll see exactly how that develops, but I think this completes our discussion of today's lecture, and I hope that this gets to you as soon as possible. And then I'll send you an email pointing out to this link. So until the next time, everyone, please take care, and I'll see you when I get back to College Park around the 10th of November.